So let's see the problem here. Consider the given reaction Ni solid give plus 4CO giving NiCO4, that is in gaseous form, and select the correct statement. Okay, formation of NiCO4 results in decrease in entropy. Okay, so if we consider this reaction, we see that on the reactant side there are 4 mole of gaseous carbon monoxide molecule, but here only 1 mole of gaseous NiCO4 is present. So the number of moles of gaseous molecules decreases as the reaction proceeds in forward direction, and that is the reason the entropy change is negative for this reaction. So formation of NiCO4 results in decrease in entropy. This is absolutely correct. Okay, coming to the next. The above reaction is exothermic. Okay, so let's see here. We know that delta G equal to delta H minus T delta S, that is the change in Gibbs free energy equal to change in enthalpy minus temperature into change in entropy. Okay, and we know that for the feasible reaction delta G must be less than 0. As this reaction is feasible, so in that case delta G must be less than 0. Okay, now in this reaction delta S is negative, so this whole term will be negative, and this negative will be forming positive. So this whole term is positive, and for delta G to be negative, this delta H must be negative, and the value of delta H must be greater than T delta S. Okay, so for this reaction delta H is less than 0, and that is the reason this is exothermic reaction. If the delta H is greater than 0, then this is endothermic reaction. So the second option, that is the above reaction is exothermic, is absolutely correct. Coming to the third statement here. Decomposition of NiCO4 is favored at high temperature. Also, if we increase the temperature, then this positive term will increase, and if we increase on further, then there will be a time that comes when this value will be greater than the value of delta H. Okay, the modulus of this will be greater than this, and if modulus of T delta S becomes greater than that of delta H, and in that case delta G will be positive and the reaction will not be feasible. So in that case backward reaction will be feasible, and backward reaction is just the decomposition of NiCO4. So NiCO4, decomposition of NiCO4 will occur when we increase the temperature. So C is absolutely correct. Now forward reaction is enthalpy driven. This is also correct, because due to this delta H term, since it is negative, then the reaction is feasible. If delta H will be positive, then in that case delta G will be positive and reaction will not be feasible. So the reaction is feasible because of this delta H, and this is less than 0, and that is the reason delta G becomes less than 0 and reaction is feasible. So this reaction is enthalpy driven, not the entropy driven. So again the fourth D option is also correct. So all the option A, B, C and D are correct for this particular question. Now coming to next problem, that is the xenon hexafluoride plus water giving A plus B, and this is the chemical reaction. If the complete hydrolysis of xenon hexafluoride occurs, then xenon trioxide plus hydrogen fluoride is the product in that case for the complete hydrolysis. If the hydrolysis is incomplete, then HF plus XeO2F2 or XeOF4 will be the product. Okay. Now, A is a monobasic acid, then A must be HF. Okay. Select correct statement. Okay. Now we have to select the correct statement. The first is A is a weak monobasic acid. Sorry, it is given here. The statement is, the first is KMnO4 can oxidize A in acidic medium. The oxidation of HF is not possible by KMnO4. Although KMnO4 is a very good oxidizing agent, but it can't oxidize HF. So the first is absolutely wrong. Coming to the next, B is dangerously explosive. This is absolutely correct. Xenon trioxide, that is XeO3, is explosive in nature. C, the total lone pairs of electron in B is 8. So let's see. This is the xenon trioxide, and we see that this is the xenon and 3 oxygen atoms. So xenon has 1 lone pair of electron and each oxygen has 2 lone pair of electron. So here overall 8 electron, 2 to 4, sorry, 4, 4, 8, 4, 12 and 2, 16. That is the 8 lone pair of electron is present. So sorry, 2 to 4, 4, 4, 8, 8 and 4, 12 and 2, 14. Sorry. So there is 14 electron present, that is 7 electron pair. We can see here 1, 2, 3, 4, 5, 6 and 7 electron pair is present on xenon trioxide. But here the total lone pair of electron in B is 8. This is absolutely wrong. Coming to the next, the shape of B is pyramidal, and this is absolutely correct. Shape is like ammonia, in which there is 3 sigma bond and 1 lone pair of electron on central atom. So the shape will be pyramidal. Okay, so option B and D is correct. A and C are incorrect. Now the next problem is, which of the following contains p pi d pi bonds? 2 p pi d pi bonds. Okay, first is xenon trioxide, and this is the Lewis dot structure of xenon trioxide, in which the hybridization of central atom is sp3. So there is no any pure vital present on xenon. So all this bond will be p pi d pi. So xenon trioxide has 3 p pi d pi bonds. So this will not be our answer. Coming to the next, this is sulfurous acid, option B, where the central atom hybridization is sp3. There is 3 sigma bond and 1 electron pair. Now sp3 hybridization, so sulfur has no any pure vital. All the pure vital of the sulfur has taken part in hybridization, and that is the reason this bond is p pi d pi, but it has only 1 p pi d pi bond. So again definitely this will not be our answer. Coming to the next, this is sulfur trioxide, and there is 3 sigma bond. There is no any lone pair of electron on sulfur because all the 6 electrons of the sulfur are used here in formation of these bonds. So hybridization is sp2. So 1 p pure vital is left on the sulfur, so it will form 1 p pi bonds, and other 2 pi bonds will be of p pi d pi nature. So C is one of the answer because it has 1 p pi bonds and 2 p pi d pi bonds. Coming to the next, that is the chloric acid HClO3, and again we see that this is the Lewis dot structure. There is 1 lone pair of electron on chlorine, and there is 3 sigma bond, 1 lone pair. So hybridization of chlorine is sp3. Again the chlorine p orbital, okay, all the p orbital of chlorine has taken part in hybridization, so there is no any pure p orbital present on chlorine. So all these two pi bonds will be of p pi d pi nature. So SO3 and chloric acid both contains two p pi d pi bonds each. So option C and D are the correct answer for this. Now coming to the next problem, and the problem is the most basic nitrogen is, we have to find the most basic nitrogen in this molecule. So there are 4 nitrogen, 1, 2, 3 and 4. So let's check here. This is the structure. Okay, so basically we see that this lone pair is taking part in resonance because this is aromatic ring. So the lone pair is delocalized here, so it will not be available for the H plus. So this nitrogen is not basic. Again, this lone pair is delocalized over here, so again this lone pair will not be available for the H plus. Now coming to the next, again there is delocalization taking place, so of course this will not be basic, but this is the pyridine ring, and we know that in pyridine lone pair of nitrogen is not taking part in resonance, that is localized on this nitrogen atom. If we do resonance, then there will be pi bond, and we know that pi bond does not exist in ring, that is lower membered ring, due to Ringsten, very high Ringsten, and the lone pair of nitrogen will be available on this, and that is why this nitrogen will be most basic. Now let's see the next problem. Which benzene ring in the given compound is more reactive in electrophilic aromatic substitution reaction? So this is the two rings here, and clearly we see that this is the ester function group, and this C double bond O acts as a minus M for this ring, and this oxygen acts as a plus M for this ring. So this oxygen gives electron to this ring by mesomeric effect, and electron density will be more in this ring, and here this C double bond O group acts as a minus M group, and it's withdraw the electron by resonance, and that is why electron density will be low in that case. So electrophile, that is electron deficient species, would like to attack on those ring where the electron density is more, so definitely it will attack on this ring. And this is since ortho-para directing group, so electrophile would like to either attach to this two position or this para position. So the most probability is this para position because there is very less steric hindrance. So the correct answer is ring 2. Now the next problem is the ionization potential of O2 is similar to that of. The flat answer is Xe, that is a xenon. A scientist named Neil Bartlett of University of British Columbia first discovered that by this observation. Okay, he first formed this compound, that is O2 plus PtF6 minus, that is the complex compound here, in which he found that the ionization potential of oxygen is 1175 kilojoule per mole. Okay. Now, the ionization potential, he thought that the ionization potential of xenon is just comparable to that, and that is 1170 kilojoule per mole, that is even lower than that. So he thought that maybe this compound can be formed in that way, and he just did a reaction. He did a reaction with the xenon and PtF6, that is so xenon and PtF6, and it forms xenon plus PtF6 minus, and this complex is also found. As a result of this, he discovered that the both of these O2 as well as xenon has similar ionization potential, and hence after that the chemistry of xenon came into light, okay, by this important observation or discovery. So the ionization potential of oxygen is similar to xenon, so option C is the correct one.